In this example problem, we're going to determine the distribution factors for the bridge shown below. We have 6 bulb T-beams, and you can see the spacing and some of the other properties of the bridge. So distance from the edge of the barrier to the center of the exterior beams. And we also have our span details. So we have 70-foot spans for the beams. And we also have the cross-section details for our FIB 36. So it's a Florida I-beam with a 36-inch depth. And we're given some of the section properties there. And we're given our details for our deck. We have an 8-inch thick deck, and the width of the deck is equal to the beam spacing of 8 feet. So the first thing that we'll do is we can calculate the number of design lanes according to AASHTO LRFD equation here. So we have a 44-foot clear roadway width divided by 12 feet per lane, which will give us 3.67 lanes. And we're going to round down, so we're going to say we have 3 lanes. Our next step is to find our longitudinal stiffness parameter, K sub G. And to do this, we'll need to find the stiffness of our deck concrete and the stiffness of our beam concrete. We're going to use our equation given in AASHTO. So here we'll find the first one. The deck concrete stiffness is 120,000 times our K1, which we're assuming is 1.0. If we don't have any given information on our aggregate or any testing information or modulus test information for our concrete, we'll just use a 1.0 there. The weight of our concrete is 0.15 kips per cubic foot. This is to the 2.0 power, and then times the concrete strength, 4.0 KSI to the 0.33 power. So we'll get this to be 4,266 KSI. So just remember that in AASHTO, in the AASHTO LRFD bridge design specification, we use KSI. So we can do the same thing for our beam concrete stiffness with a strength of 8.5 KSI, and we'll find our beam concrete stiffness there. Next, we can find our modular ratio. And our modular ratio here is the ratio of our beam concrete stiffness to our deck concrete stiffness. So we'll have 5,471 KSI divided by 4,266 KSI, which will give us a modular ratio of 1.28. So we can find our deck eccentricity from the previous slide. Our YT, the distance from the centroid of our beam to the top, is 16.49 inches. That was given. And then the distance between the top of the beam to the centroid of the deck is just half times the deck thickness, so 0.5 times 8 inches, or which will give us a total of 20.5 inches. We can use these values then to find our longitudinal stiffness parameter, K sub G. So we have N of 1.28 times our IG, 127,545 inches to the fourth, plus our AG, 806.58 inches squared, and then times our EG squared, 20.5 inches squared. And this will give us a kg of 597,133 inches to the fourth. So that is our kg that we'll use in our distribution factor equations. Next, we need to determine what
type of bridge to use for our distribution factors. So we can go to our table from AASHTO 46221-1 and look for our typical cross section. Here we have precast concrete bulb T section with a cast in place deck. So we have a type K bridge. So this is what we'll use in our or define our distribution factors. So next we can look through the different tables in AASHTO for our different distribution factor equations. And the first that we will come to is our moment for an interior beam where we have more than or equal to 2 lanes. So that's the equation that we have here first. So for this equation, we can plug in our known values. So 0.75 plus our beam spacing in feet. So 8 feet divided by 9.5, and this is to the 0.6, times our beam spacing again in feet divided by our span length, 70 feet, and this is to the 0.2 power. And then we have our K sub G, so 597,133 inches to the 4th. So we'll keep that in inches divided by 12 times our length in feet, 70 feet, times our thickness, our slab thickness in inches, 8 inches to the 3rd. And this is all to the 0.1 power. So solving this, we'll get our distribution factor equal to 0.679 lanes per beam. So next we can find our shear distribution factors for interior beams if we have more than 2 lanes. So plugging in our values into the equation from our AASHTO table, we'll get 0.2 plus 8 feet divided by 12 minus 8 feet divided by 35 to the 2.0 power. And we'll get our distribution factor here to be 0.814 lanes per beam. So we can use then these distribution factors then to design our interior beam for moment and shear and figure out the actual load that we should apply to a single beam when designing for moment and shear. So we can do the same thing then for our exterior girders. And the first girder here that I'm showing is our, the first equation here that I'm showing is for the moment for an exterior beam where our number of lanes is greater than or equal to 2. So we'll use our interior moment times this E, and the E can be found using the equation here. So our E is equal to 0.77 plus D sub E divided by 9.1, where D sub E we can find, as shown here, the distance between the outside of our barrier to the inside of the barrier to the center line of our exterior girder. So we'll find our E to be equal to 0.990. So taking our 0.990 times our distribution factor we found before, we'll get a value here of 0.672 lanes per beam for our exterior beam. Next, we can find the distribution factor for the shear of our exterior girders. So here, our distribution factor for shear of exterior girder is again dependent on an E times the distribution factor for the interior girder for shear. So our E we can find using this equation, and our D sub E defined the same way, and we'll get our E to be equal to 0.8. So taking 0.8 times our shear distribution factor from before will give us a distribution factor for our exterior girders of 0.651 lanes per beam. So again, we can remember that these distribution factors would be used to take the total bridge demand and divide it to a single interior or exterior beam.
So we would use these then to design our typical exterior beam and our typical interior beams. For this specific case, the table doesn't ask for the lever rule to be used, but there are many cases where the lever rule is or should be used to find the distribution factors. So the next portion of the example, we're going to use the lever rule to find our distribution factors. The first thing that I wanted to highlight is we have a multiple presence factor that takes into account the likelihood of multiple lanes being loaded to their most severe load at the same time. And the distribution factors automatically include the multiple presence factor. If we're using the lever rule, we need to take the distribution factor we find using the lever rule times our multiple presence factor to find our final distribution factors. So I give us our multiple presence factor in this table here from AASHTO, the section that I highlight. And remember that this multiple presence factor, again, it takes into account the likelihood that trucks will be present in adjacent lanes on a roadway at the same time. So with one lane, you're likely to have, you'll have one truck in that lane. But as you get more lanes, it becomes less likely that all of the lanes are going to be loaded or have the maximum load at the same time. So you can see the multiple presence factor decrease. Some other notes. So multiple presence factors are already included in the distribution factors. And remember that the factors should not be used in the fatigue limit state. So in the fatigue limit state, you would need to divide the distribution factors by the multiple presence factor, or you don't take the lever, or you don't take your lever rule result times the multiple presence factor. When we use our lever rule, we're going to place a hinge over each of the interior girders. So we'll place the hinges there, and then we'll place our truck load as far to the left as we can. So we'll have the spacing or the placement of that first wheel 2 feet from the edge of our barrier, and then the spacing of the next load 6 feet away from that. So that's the placement of the load for our single lane. So with the load placed there, we can solve for our reaction at A, and that'll be our distribution factor for our exterior girder with a single lane load. So solving our moment, summing all of our moments about point B and setting them equal to 0, we'll have R sub A times 8 feet minus P over 2 times 8 feet minus P over 2 times 2 feet set equal to 0. And solving for RA, we'll get a reaction here of 0.625 times P. We have a single lane here, so our multiple presence factor M is going to be equal to 1.2. So we can find our distribution factor, including the multiple presence factor, by taking 1.2 times 0.625, which will give us a value here of 0.75. So if we use the lever rule, we find the distribution factor for moment and shear the same. So this would be our distribution factor for a single lane load for moment and shear for an exterior girder. Next, we can use the lever rule again for an exterior girder, but this time with multiple lanes being loaded. So here we have two 12-foot lanes, and we can have our truck wheel loads oriented the way that I'm showing. So as close to the left edge of this lane as possible, 2 feet. And again, here the truck as close to the left side of the lane as possible, 2 feet, and then a 6-foot spacing between the two adjacent lanes. So again, we're going to sum our moments about B and find our reaction at A. And remember, we have a hinge here at B. So our moments again will be the same as we found before. So our R sub A times 8 feet, and then minus P over 2 times 8 feet minus P over 2 times 2 feet. And sum our moments, set them equal to 0, and solve for RA. And we'll get our RA equal to 0.625 times P. For 2 lanes, we'll have a multiple presence factor equal to 1. So we have 1.0 times 0.625 is just going to be 0.625. So yeah, note that only the wheels from the outside truck are going to influence the outside segment here. Next, we can find the distribution factors for our interior girders with a single lane and multiple lanes. So we'll start with a single lane. We can place our truck to have a maximum force effect, and we can use our influence line for knowing where to place the truck and also for determining the magnitude of the reaction at one of our interior girders. So the magnitude of the reaction at RC, we'll get a maximum effect if we place 1 point load at RC and 1 point load 6 feet apart. So 6 foot is the wheel spacing again. And then we can find the magnitude of the load by taking the magnitude of each one of these point loads times the height of the influence line at that point. So we'll have 0.25 times P over 2 plus 1.0 times P over 2. And this will give us a value here of 0.625 P. So again, this is for a single load, so we'll take our value there times 1.2 to include the multiple presence factor. So 1.2 times 0.625 will give us a factor here of 0.75, so distribution factor of 0.75. So again, this is an interior girder with a single lane loaded. Next, we can find our distribution factor of an interior girder with multiple lanes loaded. So again, we'll use our influence line for placement of the loads and determining the magnitude of the reaction. And we can find that if we place the loads with our lanes in this configuration, where we have one load immediately over the beam line, our spacing is 6 feet there, so the spacing of one truck in that lane, and then 2 feet, 2 feet, so the closest that a wheel from a truck can be is 4 feet away. And so those 3 loads are going to influence the reaction at C according to our influence line. So we can find the height of our influence line at our 3 different load points, as I'm showing here. And the reaction will just be the magnitude of each one of the loads times the height. So we have 0.5 times P over 2 plus 1.0 times P over 2 plus 0.25 times P over 2. And this will give us a value of 0.875 times P. So we have 2 lanes loaded, so our multiple presence factor is going to be 1.0. We have 1.0 times 0.875 will give us a value here of 0.875. So for most cases, we'll use multiple lanes loaded for interior girders and a single lane loaded for exterior girders. On this slide, we have a summary of the results from this example. So the first table here is the distribution factors using the AASHTO LRFD bridge design specification tables. So these would be the factors you would use for the moment and shear for interior girders and the moment and shear for the exterior girders. For our distribution factors that we found using the lever rule, we can use the maximum of our single and multi-lane distribution factors. So we would use the single lane distribution factor here for exterior girders and the multiple lane distribution factor for the interior girders. And these distribution factors we can use for both shear and moment. The last part of this example, I wanted to highlight some different notes on some common pre-topped sections. So for our pre-top sections, we can go to categories I and J from our AASHTO distribution factor tables. And we can generally assume that we have a sufficient connection so that the entire bridge acts as a unit. With the modern connections with UHVC and cast in place joints, this will typically be the case. So the northeast extreme T or next beam is a popular double T section used for ABC applications. And the next beam details, the second edition provided from PCI Northeast, makes the following recommendations. So the first is that we can use our AASHTO cross section assuming that the deck is sufficiently connected as a unit. So I and J, or I guess we're using I, assuming sufficiently connected as a unit. We can treat each stem as an individual girder, and the stem portion is going to be the stringer of the beam, and the upper portion of that is going to be the composite deck. So you can see this section here we can use to find the I, the moment of inertia, and the EG, the distance between our stem and the center of the slab. We have our slab thickness is just the thickness of our top flange. And then we can also find our gross area and our other necessary properties from our geometry for the next beam or the stem of the next beam. So with this, I guess the next is we can use the average stem spacing for our beam spacing terms in the equations. So the average spacing between stems in precast sections and between stems of adjacent precast sections. So if we had another beam over here, the distance between those stems. And then we can use all these to calculate our distribution factors for each of our stems. And then we can combine the two distribution factors for the adjacent stems to give us our total distribution factor for one next beam. And this is what we can use in the design of a next beam. We can use a similar principle if we have a duct bulb T section where we would break up our duct bulb T and treat the top flange of the duct bulb T as the deck. The deck thickness is just the thickness of our top flange there. And then the rest of the duct bulb T beam would be the beam section. And the eccentricity E sub G would just be the distance between the centroid of our deck component and the centroid of our web and bottom flange component. So these can be used with our appropriate equations from our tables in AASHTO. So with that concludes this example.